Why don't you take the pop to your seat?
Isn't that thing?
I mean, and bring it back because it's 4 o'clock right now.
Okay.
Yeah. Okay, it's 4 o'clock. Let's go and get started. All right. Good afternoon, everyone. How's everyone doing today? Last class, last lecture, I guess, and then next week is final presentations. And so, like I mentioned on Monday, we're just going to be finishing up this section on muscle force optimization, mostly with the objective that some of you may find it useful for your final projects. Okay. So at this point, I think everyone's final project is group is pretty much settled. All the topics have been chosen. Everyone got the schedule for the final project for next week as well. And so, we're going to just be doing those next week. Okay. On Monday, I mentioned the possibility of having all of the final presentations be virtual. And so I think we are going to move forward with that. So both Monday and Wednesday are going to be just Zoom only lectures. So please plan to be online during those times, okay? Especially during your presentation times. So the way it's going to work is that only one person in your group has to have the presentation, and I'll give that person screen sharing rights, and then you can share your screen and present just like that. Okay. I think it's just a little bit easier. I think it's better for recording too, because usually when you give presentations in the class, the recording on Zoom doesn't come across that well because the audio doesn't come out, and we can't see you and everything like that. So let's do that. Okay. So Monday, Wednesday going to be virtual only lectures. Just be prepared to present. Okay. And even if you're not presenting on a day, I am expecting everyone to attend the final presentations, because remember, the whole point of the presentations is to kind of teach your classmates about your given topic, and that's kind of pointless if you don't show up to all the other presentations. So I think the temptation, is to just show up for your own presentation, then just kind of leave for other parts. But I really want you guys all to come for everyone's presentations. And learn something new, because I think this year, definitely way more than last year, I think you guys have picked some really interesting topics this year. And I'm looking forward to learning something new about some of these topics as well. So I'm hoping that, everyone can attend all the presentations as well. Okay. Okay. And so with that said, the plan for today is we're just going to finish up. We're just going to finish up that last example from last time. And then I have one more example, a little bit of a more involved example. I think maybe one that's going to be more useful for your final projects that I want to go over today as well. Okay. I don't think it'll take too long. I think we'll probably end a little bit early. And if we end early, then that's fine. This is the last lecture. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get to it. Let me scroll up here, just so I don't have to write it down again. Let me just kind of remind you of the example that we were working on. Okay. Okay. So we were working on this example here, right? And so we were given a situation where we're analyzing the foot, and what we're saying is that through some inverse dynamics analysis, or maybe through some measurements of some kind, we know that the net moment at the ankle is going to be 100 Newton meters, and that's a plantar flexion moment. Okay. And what we're interested in finding out is, what are the exact muscle forces that are required to produce this moment. Okay. And so in the problem, we're given that we have 3 muscles that work at the ankle that can produce a plantar flexion moment. So we have the gastrocnemius muscle, we have the tibialis posterior muscle, as well as the soleus muscle, right? And so their maximum force and moment arms are given as such. Okay. And then we spent the rest of the class basically setting up the optimization problem. Okay. So remember, when you're doing these problems here, any optimization kind of falls in this category. You're going to have more unknowns than you have equations, right? And so we need to have a different kind of framework, a different way to solve these types of problems, and that framework is called optimization. Okay. And so when you're solving these problems, especially if you plan on using this for the final project, the only thing you have to really do is kind of just set up the problem, and then properly set up the code, which is that's primarily what we're going to go over today, is how to set up the code to solve these problems. Okay. So for this particular example, we had one equation that must be satisfied. So this equation here is our constraint. Okay. And so we went over it last time that the total moment produced by these three muscles must be 100 Newton meters, right? And so to produce that moment, we have the product of each of the forces, Fg, Ft, Fs, multiplied by its corresponding moment arm, which is given to us in the problem. Okay, and so this summation must be satisfied in the problem. So remember, because this equation here is required to be fulfilled, this is considered a constraint of the problem. Okay. And so you're going to come across a lot of constraints, and for our purposes, you know, most of the time the constraints are going to be based on your inverse dynamics analysis. Okay. Because remember, from your inverse dynamics analysis, you're able to compute things like the net forces, X and Y forces, as well as the net moment. Okay. You know, whatever combination of muscle forces that you choose, you basically have to accomplish those net forces. Okay. And so that comprises the constraints of our problem, right? And this problem, this one's pretty simple. We only have one constraint because we're only given just a single net moment for the problem. Okay. Okay. And just like I mentioned, you know, the goal for this problem is to compute the distribution of the muscle forces Fg, Ft, Fs that are needed to complete this motion. Okay. Okay. So the majority of the time we spent last time was talking about this idea of an objective function, right? And so the objective function is a function that you have to define. This is usually not given to you in the problem, but this is an equation that you can use to basically tell the algorithm or tell you know, the optimizer how you want to distribute the muscle forces. Okay. And the idea is to basically give a mathematical way to rate certain solutions as better than the other ones. Okay. Okay. And so there are a couple ways that we can formulate our objective function. Okay. So this is the first one that we went over, where the objective function in this case would just simply be the sum of all the forces, right? And so we just add together Fg, Fs, Ft. Okay. And what we want to do is we want the optimizer to minimize this quantity. Okay. So that's basically how the optimizer is going to solve for our solution. If we give an objective function and we say that find the values for each of the variables here that minimize this overall function, okay, while still kind of obeying the constraints. Okay. And so if we do this, you know, we end up with kind of somewhat of a trivial solution, right? And so we end up choosing a solution where the muscle force with the largest moment arm does all the work, right? And so that in that case, that was the gastrocnemius muscle. And so we end up with the Fg of 2,564. Okay. And this is one that satisfied the constraint. But because this one is the most optimal one, it has the lowest value of the objective function. This is the one that the body is going to choose. Okay. So I did this not as an example, you know, not really as something that's actually kind of feasible in practice, right? Because we know that in reality, you know, whenever you perform a motion, it's never just one muscle doing all the work, right? We have we have a combination of the different muscle forces that contribute to a motion, right? So this solution right here, even though it seems optimal and it satisfies the constraints, is not one that is reflective of reality, okay? And so what that tells us is that we have to change our objective function to make sure that it reflects reality in a better way, okay? And so what we came up with was something like this, right? And so instead of just taking the sum of the forces, we're taking the sum of the forces squared, okay? So we take Fg squared plus Ft squared plus Fs squared, right? And another thing we're doing is we're normalizing these forces as well. So we're dividing each of these forces by the respective maximum. Okay. Okay. And now instead of minimizing that function above, we're now minimizing this function right here. Okay. Okay. And so even though it looks similar, right, it's mathematically looks kind of similar to the other one where we had just some of the forces, those squares actually make a big difference, right? And so if you actually solve this problem using MATLAB, you end up with the following solution, right? So you get FG is equal to 820, FT is equal to 93, and FS is equal to 1868.2, okay? So this right here is a much more realistic distribution where you have kind of, multiple forces acting. They're kind of splitting the load in between. Okay. So this objective function here is one that's a little bit more realistic. And if you were to apply muscle force optimization to your final project, one that's of this form is usually a good starting point. And in fact, the second example that we're going to do today has this exact same form as well. Okay. Okay, so that was just kind of a very quick recap of last time. And the reason I kind of recapped it from the beginning was because the next thing I'm going to show you is the MATLAB code. And so I'm going to show you how to actually set this up in MATLAB to solve it. Okay, but before I do that, are there any questions on this example here? Okay, all right, so let's go ahead and jump into the MATLAB code. Actually, before I do, let me mention a couple things that you're going to need to do. Okay. So the nice thing about MATLAB is that they have a big suite of optimization tools, okay, that you can just kind of call just as a function. The difficulty with using these routines is that they are not the easiest to use, right? And so even though the way I say it here is that we have a built-in function, we just have to call it. You still have to feed it the appropriate arguments. You have to feed it the appropriate variables in order for it to run, and that can be very tricky if you've never done that before. And so that's kind of what we're going to go over today. Okay. All right. So the first thing, if you are planning to run this at home, you have to install actually what's called an add-on to MATLAB. Okay. Okay. And that add-on is called the optimization toolbox. Okay. And so if you've never done this before, if you've never added an add-on onto MATLAB, this is basically how you do it. And so from the main MATLAB console, from the main window, okay, you're going to click on Home, then Add-ons. Okay. So what this is going to do, this is going to open up a new window. Okay, it's almost like kind of like an app. It's like an app store, but for MATLAB. Kind of a funny thing. Okay. Okay, and then from that new window, from the App Store, you're just going to use the search bar and search for optimization toolbox. Okay, and then you just there'll be a button to install it or to add it, and so you'll just do that. Okay. So it's not a default feature in MATLAB. Even though this toolbox actually is developed by MathWorks, you do have to add it in. Okay, and if you buy MATLAB yourself, this may be something you have to pay extra for. But if you're using a school license, if you're using your student account, this is something that you get by default. Okay, but you need to make sure that you add it. So this toolbox here is going to give us the functions that we need to run it. Okay. All right. So the example that we just did, I've already implemented a MATLAB solution for it. It's posted on Canvas. Okay. And the file is called muscle_force_optimization. _example _1.m. Okay, so that's the file we're going to be looking at. Okay, but I want to give you the name of the file just so that you can look it up later. Okay, so let me go ahead and bring it over to the desktop here. Unfortunately, because this entire semester this computer's been broken, and so we don't have access to MATLAB itself, but I can show you the code. Okay, and we're going to go through this code kind of line by line. So let me go ahead and zoom in a bit. Okay. All right. So let's break this code down. And so I think the only annoying thing about this is that we don't have MATLAB's coloring, and so you'll just kind of have to go just based on the symbols here. Okay. Okay. So I've broken this code up into several different sections here, where each section is going to define a different part of the code. Okay. And I've added a bunch of comments here to kind of tell you what's happening in each section. Okay, so section 1 right here. So section 1 is to define the maximum force limits for each of the muscles, right? So if you remember from the example that we did, each of the forces that we were looking at has a maximum amount of force that it could exert based on its cross-sectional area, right? And so the maximum force for FG, the gastrocnemius, is 4,097. The maximum force for FT is 3,052. The maximum force for FS is 6,435, okay? So these were all given to us in the problem. And all I'm doing here is just defining new variables here that are going to store these values. Okay. Okay. Section 2. So section 2, we're going to define the objective function that we're going to use to minimize metabolic power consumption. Okay. And to do this, we're using what's called an inline function in MATLAB. Right. So if you've never used an inline function before, basically it defines this hand that we call this a function handle. And we're going to be able to call it later to compute the objective function. Okay, so the syntax for this is that we have obj_function is equal to we have an @ sign. Okay, and then after the @ sign we have parentheses, and so inside these parentheses are going to be what's called the input arguments for this function. Okay, so that's what we're going to feed in, and then inside here we're going to compute the output. Right. And so remember, our objective function here is we have our 3 forces. So we have F parentheses 1, F parentheses 2, F parentheses 3. Okay. Each one we're going to divide by its respective maximum, and then we're going to square it. And then we're going to add all of them together. Right. So this is this part right here. Even though the syntax looks a little bit scary with the @ sign, This is simply just the objective function. Okay, so this is what we went over in the code, in the notes. Okay, section 3. So section 3 here, we're going to define our constraint. Okay, so remember the constraint in this case was we were forcing our forces, our muscle forces here to produce a net moment of 100. Okay, and so to do this, I'm defining two things. So on the one hand, I'm defining a variable that defines the moment that we need to exert. So that's 100 Newton meters. Okay. I'm also defining a vector here to hold all of the moment arms for each of the muscles, right? So this is the moment arm for the gastrocnemius force. This is 0.008. This is the moment arm for the tibialis posterior. And then we have the 0.036. So that's the moment arm for the soleus muscle. Okay. Okay, so that's section 3. So sections 1 through 3, these are all things that are kind of defined for us already in the problem. All we're doing is just kind of putting it into the code. Okay. All right, section 4. So section 4 is to define what's called the initial guess for the muscle forces. Okay. So remember the way that an optimization algorithm basically works is that it's basically going to perform a guess and check, right? And then based on what it guesses, it's going to improve upon that guess. That's in a very brief nutshell. That's basically how optimization works, right? But in order for it to start, you actually have to give it an initial guess. Like you have to give it a starting point. It doesn't matter how bad the starting point is. Sometimes it does matter, but for this case, it doesn't matter all too much. Okay. And so we're going to start with a very simple solution of Fg is equal to 1, Ft is equal to 1, and Fs is equal to 1. Okay. So all the forces are equal to 1 Newton. This is obviously going to be not correct, right? So this is obviously not an optimal result. This is just a starting point. So you have to kind of give it a dummy, almost like a dummy value for the starting point. Okay. And then what we usually do is we typically save all 3 of these guesses into a single vector. So that's what this F0 vector is right here. Okay, section 5. So section 5, we're going to set the upper and lower bounds for each of the design variables. Okay, so these are going to be the upper and lower bounds for Fg, Ft, and Fs. So the lower bounds for all these forces is going to be 0. Okay, so we have 0, 0, 0. And then the upper bounds for each of these forces are going to be Fg max, Ft max, and Fs max. These are the variables we defined earlier in terms of the maximum values for those functions. Okay. And then finally, we have section 6. So technically, section 6 is the end of it. From here, section 7 is just some additional stuff, which I'll explain in a second. But up until section 6, this is everything that you need to do to run just one optimization. Okay. Okay. So section 6 here, we're finally going to call the optimization function, and the name of the optimization function is called fmin_con. Okay. So that stands for minimize our function f in a constrained manner. And fmin_con takes a lot of different arguments. And so after fmin_con, you're going to put an open parentheses, and then you're going to add the following variables here, right? So first thing you're going to do is you're going to provide the handle for the objective function. Okay, so that's what we define in section 2. Okay. Next, we're going to give the initial guess. So the initial guess is what we define in section 4. Okay. You're going to have two sets of blank brackets here. Okay. So those brackets are for different kinds of constraints called the inequality constraints. Okay, we don't have those in this problem. We only have an equality constraint, so we just pass empty vectors there. Okay, these next 2 vectors go together. So we have a moment arm vector and a joint moment vector. So these 2 vectors here define the what's it called? The equality constraint. So this was in section 3. Okay, and then the lower bound is obviously the lower bounds for each of the variables, and the upper bound is the upper bounds for each of the variables. Okay. All right, and so you would run this code, and then at the end of this code, this fopt1, this is going to contain the optimal values for each of our 3 muscle forces. Okay. Okay. So basically, the way that you use this code is that we want to run this function right here. So this function is called fmin_con. And we're just kind of setting up all the input arguments for it. So the objective function, the initial guess, the constraints, and the upper and lower bounds. Okay, so that should kind of be your mindset if you're going to be writing an optimization code here. Is we just want to set everything up for the function, and you want to make sure that you define all the variables as needed for that function. Okay. Okay. Questions on this? Okay. And I wish I could run it because I think it would be really interesting to run here, but this computer doesn't have that app right now. Okay. All right. So section 7 right here, I'm basically running the optimization over and over again, but I'm doing it for different moments. Okay. And so this is actually going to produce a plot in terms of, you know, how all the muscle forces change if you change that moment. Okay. So this is kind of just a fun thing, just to plot it, just so that you can see. Okay. Okay, all right, so that code is available to you online. So it's ready to go as it is. So you can run this code and check the results. Although, of course, if you want to apply this to your final project, you're going to have to change things in this code to match your own free body diagram, your own muscle forces, and things like that. Okay, and if you want to apply this to your final project, but you're having trouble kind of you know, setting up the code, definitely let me know. Come to office hours, and I'm more than happy to help you out with this stuff. Okay. All right, final questions on this before we move on to the next example. Okay, all right, so let's look at the next example. So the next example is primarily going to be a coding example as well. So I have another example code for that. But let's set up the problem first on paper, and then we'll talk about its implementation in code. Okay. So this next example here is going to be a lot more complicated. And this is kind of probably be more typical of what you would do for your final project. And I don't know why this thing is frozen. Sorry about that. There we go. Okay. Okay, so this one, we're going to look at the entire lower extremity. So we're going to be looking at 9 different muscles here, and we want to basically solve for the muscle forces during a running motion. Okay. Okay. So this is going to be a total of 9 different muscles. Okay. And what's also going to be new about this example compared to the previous one is that we have not just one joint, but we're going to be spanning 3 different joints here. Okay. And so those joints are the hip joint, the knee joint, and ankle joint. Okay. All right, so let's go ahead and draw the figure for this, and this is probably going to be the most time-consuming part. Okay. All right. So this part right here, that's going to be the hip, and that's going to be connected to the thigh. Okay. So this right here is the thigh. Right, and then the thigh is going to be connected to the lower leg or the shank. Okay. And then this is connected to the foot. Okay. And so the position of this of the lower extremity is going to change as a function of time, right? And so, you know, that's the whole idea with motion. But we're going to be looking at it at just a single snapshot in time. Okay. All right. So let's look at the 9 muscles that we're going to be looking at in this example here, and we'll go from the top bottom. Okay. I'm going to try to use different colors here to make it a little bit easier to read because the figure is going to get a little bit messy. Okay. Okay, so we have one muscle that attaches kind of from the top of the hip down to the upper thigh. So this right here is the gluteus maximus. This has a maximum force of 3,316 newtons. Okay. And just like the previous example, we're going to be writing out the moment arm for this muscle as well. But because we're spanning multiple different joints, what you're going to see is that some muscles actually can affect multiple joints. And so some of these muscles will have multiple moment arms. So one for one of its joints and one for the other joint. Okay. So for the gluteus maximus, it's only attached to one joint, which is the hip joint. Okay. And so its moment arm for that is going to be a minus 5.6 centimeters. Okay. So notice I put a negative there, right? And so it's not that it's a negative length. Negative lengths don't really exist. But I'm using the signs there to indicate the direction of the moment that this muscle is applying, right? Because some muscles will apply kind of a clockwise moment, some will apply a counterclockwise moment. Okay. And so that negative there kind of takes care of that. And so we don't, in this particular problem, we don't have to worry about the sign convention because that's going to be given to us directly by the moment arms. Okay. Okay. So that is the gluteus maximus. Okay. So the next muscle is going to be the hamstring muscles. So that's going to attach from the basically from the hip down to the shank. Okay. So it's going to be something like this. So this is the hamstrings. Let me label these two. So this would be muscle 2. Gluteus maximus would be muscle 1, just to make things a little bit easier for us. Okay. So the hamstrings have a maximum force of 3,744 newtons. Okay. It has 2 moment arms, one moment arm at the hip and one at the knee. So its hip moment arm is a minus 5.4 centimeters, and its knee moment arm is going to be a positive 4.2 centimeters. Okay. Okay. Next, we have another muscle that kind of crosses over just like that. So this muscle here is going to be 3. This is going to be the biceps femoris. Okay. This has a maximum moment of 1,369 newtons. Okay. It has 1 moment arm at the knee, which is 3.5 centimeters. Okay. Okay. So that takes care of basically all the hamstring, posterior leg muscles, posterior thigh muscle, I should say. Okay. Let's come on back up. So let's go back up to the hip here. We have another muscle that kind of attaches, from the front of the hip to the front of the thigh. So this is going to be muscle 4. Okay. This is called the iliopsoas muscle. Okay. This has a maximum force of 4,237 newtons. Okay. It has 1 moment arm at the hip, which is 4.3 centimeters. Okay. Okay. Now we have a couple quadricep muscles. And so we have one muscle that attaches kind of in the same point on the hip, but then goes all the way down to the knee. Okay. Okay, so this would be muscle 5. So muscle 5 here is the rectus femoris. Okay. This is 2,328 newtons. Okay. It has two moment arms. One at the hip, which is 4.9 centimeters. Okay. Another at the knee, which is a minus 4.9 centimeters. Okay. By the way, these numbers here aren't just being made up. These are actually taken from actual measurements. Okay. Then we have the lower frontal thigh muscle, and so that is the vasti muscle, and so that is kind of attaches like this. So the vasti muscle is a pretty beefy muscle. It has a maximum force of 8,655 newtons. It has a single moment arm at the knee for minus 4.4 centimeters. Okay. Okay. So those are all the muscles in the upper leg. Okay. Now we come down to the lower leg, which is going to be the calf and the front of the shank. Okay. So a couple of these are familiar. They were from our previous example. And so one of these being the gastrocnemius muscle. So gastrocnemius kind of attaches on the back of the knee and goes all the way down to the ankle. Okay, kind of like that. So 7 here is gastrocnemius. Okay. This has a maximum force of 4,097 newtons, just like before. It has 2 moment arms, one at the knee for 1.9 centimeters, and one at the ankle, and that's a minus 3.9 centimeters. Okay. We're gonna go through the whole rainbow here. Okay. And then at the lower shank, we have the soleus muscle. So the soleus muscle kind of attaches near the middle of the shank. It comes down to the ankle, just like that. Okay. So this is the soleus muscle. This is muscle 8. So the soleus muscle has a maximum force of 6,435 newtons, has a single moment arm at the ankle of minus 3.6 centimeters. Okay. Okay. And then the final muscle that we're going to consider attaches like this. Okay. This right here is the tibialis anterior muscle. Okay. A relatively small muscle. Most of the muscles in the front of your shank are pretty small. Okay. So this has a muscle force of 1,207 newtons. It has a single moment arm at the ankle of 4.5 centimeters. Okay. All right. Let me kind of move this. Oops. Oops. Let me kind of move this to the next line here. Okay. All right, so those are our 9 muscles. And so even just writing the diagram for this took us about 15 minutes to do. So, you know, this is obviously a problem that you can't solve by hand, right? 9 different muscles here, each with multiple moment arms and each have their own maximum minimums. So this is definitely one where we need to use the computer with, okay? But this is really cool. And so even though, you know, if I showed you a figure like this at the beginning of the semester, this would be really intimidating. It kind of still is a little bit intimidating right now, but you know, now that we've kind of reached this point in the class, you know, we've learned a lot, and we're equipped to kind of solve something like this, you know, with the help of MATLAB and muscle force optimization. Okay. Okay, so our goal here is going to be exactly the same as before. So, you know, for this configuration right here, you know, we're going to be given, we're going to be given kind of the net forces and net moments at the hip, the knee and the ankle joint, okay? And we want to compute, what are the muscle forces that are needed to produce these forces and moments, okay? Okay, so that was a lot of drawing. We have a whole bag of Skittles here on the screen. Any questions on this so far? Okay, all right. So let's go through the setup in the MATLAB code. So I'm gonna start here on the iPad, just because the formatting of some of this stuff gets a little bit tricky, and it's a little bit easier to explain it here on the iPad before jumping into the code. Okay. So in this case, we want to compute. So we want to compute the muscle forces for each of the 9 muscles, okay? All right, and so we're going to be given, net forces and net moments at the ankle joint, the knee joint, and the hip joint, and then that's going to give us all the information we need to solve for the muscle forces. Okay. Okay. So we'll get to that. We'll get to that in a second. We are going to first define our objective function. Okay. Remember, the objective function, this is the function that we're going to try to minimize through the optimization process, right? And so, the constraints are only going to get us so far. In fact, in this problem, I think we're only given three constraints. Okay. And so, we need the objective function in order to find all the other muscle forces. Okay. Remember what we talked about last time. The way that you define your objective function should reflect some kind of physical property of the system that it naturally likes to minimize. Okay. Because in situations like this, there are going to be multiple, sometimes infinite amounts of solutions, right? Remember that from the previous example where, we looked at some trivial solutions where we said, if we assume that one muscle was doing all the work, then we can find some solutions, but that wasn't necessarily reflective of reality, okay? And so your objective function here should be some physical quality that you want to minimize, or some physical kind of characteristic of the system, okay? Right. In other contexts, these are for students who are in my 454 class. Oftentimes we pick the objective function to reflect things like the overall cost of building a structure, right? And so oftentimes when you're designing an engineering structure, you want to minimize that cost. And so you can use optimization to find out, how do you do this in the most cost-effective way, okay? And you can write your objective function to reflect that. The human body is a little bit different, and so the human body doesn't. It's not a vending machine. You can't put money inside your inside your body. But the currency that typically is used within the body is energy and power. Okay. Okay. All right. So to that end, we can make our objective function have a similar form to our previous one, right? Because what we said was that the metabolic energy consumption for muscle is roughly proportional to the muscle force squared, right? Not exactly, but it's pretty close. Okay. Okay. And so our objective function should probably have the same mathematical form if we wanted to kind of optimize over energy consumption. Okay. And so to that end, our objective function will look like the following. Keep in mind that we have 9 forces here. So we need to have 9 variables in this problem. Okay. So we have F1, that is the gluteus maximus force, divided by F1 max, quantity squared, plus F2 divided by F2 max, quantity squared, plus F3 divided by F3 max, quantity squared, plus F4 max, quantity squared. Okay. Let's write out all 9 terms. Couldn't fit it on 2 lines. This looks very long, but remember, we're having MATLAB compute all of these things. And so, you won't have to actually plug into this formula. MATLAB is going to do it for you. You just have to kind of set up that formula within MATLAB. Okay. But this is good. So this kind of forms the same, has the same kind of relationship as before, one that we can optimize over. Okay. Okay. Now let's talk about the constraints. Okay. Okay. And so our constraints in this case are going to be, we're going to have 3 constraints. Okay. Remember, we mentioned earlier today that the constraints for a biomechanical optimization typically come from an inverse dynamics analysis, right? So remember, you usually run muscle force optimization after inverse dynamics. Okay. So from inverse dynamics, let's say that we've measured the net moment at each of the joints. Okay. And so we have a net moment at the hip, M hip, the net moment at the knee, M knee, and we have a net moment at the ankle, M ankle. Okay. And remember how we compute this. And so the net moment at the hip, okay, that's going to be equal to, okay, it's going to be equal to the summation of the specific force Fi multiplied by Ri. Okay, where I goes from 1 to 9, and this Ri here, this is the moment arm for that muscle at this joint, which in this case is at the hip joint. Okay. Okay. So remember how some muscles here had multiple moment arms, right? And so we're going to incorporate that. So some muscle forces are only going to show up in one equation, and so those are the muscle forces that have just one moment arm. But for the muscles that have two moment arms, they're going to show up in multiple equations here. Okay, and so for each of these moment equation, or each of these net moments, they're each going to give us a different equation. Okay, so we have equation 1, equation 2, equation 3. Okay. So we have 3 constraint equations here for our 9-dimensional problem. Okay, 3 constraints for 9 design variables. Okay, I'm going to write out the first. I'm going to write the first equation here in its entirety, just to kind of show you what I mean. Okay, and throughout this time, refer back to the figure that we drew before, and keep track of which muscles here have a moment arm at the hip. Okay, so that's going to be F1, the gluteus maximus. It's going to be F2, the hamstrings. F3 does not act at the hip. F4, the iliopsis. F5, the rectus femoris. F6 does not act at the hip. 7 does not. 8 and 9 do not. Okay, so you have F1, 2, 4, and 5. Okay. Okay, so we have M hip is equal to. We have F1, R1. So this right here is the gluteus maximus. Okay, plus F2, R2. This right here is the hamstrings. Okay, plus F4, R4. Okay, this is the iliopsis muscle. Okay, and then we have F5, R5. This is the rectus femoris muscle. Okay, nothing else acts at the hip. Okay. Of course, all of these moment arms are given to us, and so we can go ahead and plug those in, right? Some of these are negative, remember, because they're acting in the opposite direction. So you have M hip is equal to a negative 0.056 times F1 minus 0.054 F2. Okay. So the moment arms for both the gluteus maximus and the hamstring are negative. So that means they apply moment in the clockwise direction. Okay. Next, we have the iliopsis muscle, which is going to be a positive 0.043 F4 plus the moment arm for the rectus femoris, which is 0.049 F5. Okay. All right. So that's our first constraint equation there. Okay. And it comes just straight from the measurements. Any questions on this so far? Okay. All right. I'm gonna put this in another form though, one that's gonna be a little bit more convenient. Okay. Let me do it like this. And so we're going to say mHIP. If you've used MATLAB or if you've been in any other of my classes this semester, you know what's coming. We're going to put this in matrix form or vector form, okay? Because MATLAB is kind of designed from the ground up to work with matrices. And so, you know, if you're going to be using MATLAB, you're just going to be using vectors and matrices, okay? All right, so it's going to be negative 0.056, negative 0.054, 0.043, 0.049, okay? And we're going to multiply this by the vector f1, f2, f4, f5, okay? So all I did was I took our linear equation here and just separated out the coefficients and the variables, okay? Okay. I'm going to do one more step here. And so even though this equation here only involves 4 of the unknowns, you know, let's expand this a bit further to include all 9 muscles, okay? With the catch here that if the muscle does not appear explicitly in this equation, we're going to give it a coefficient of 0. Okay. Okay, so we have mHIP is equal to minus 0.056. That's going to be for F1, minus 0.054. That's going to be F2. Okay. Next is F3. F3 does not show up in this equation, so we're going to give it a coefficient of 0. Okay. Next, we have the coefficient for F4, so that's 0.043. The coefficient for F5 is 0.049. Okay. Now we have F6, F7, F8, F9. None of those appear in this equation, so we're going to leave those coefficients at 0. Okay. And then we're going to multiply this by a vector that has all of the forces. We have F1, F2, F3, F4, F5, F6, F7, F8, F9. Okay. All right, so we basically separated this out. So what we have here is a vector of all the moment arms. Okay. And then this column vector here is a vector of all of the unknown forces. Okay. When you multiply these two together in this exact form, this is going to give you that constraint, right? Okay. All right. So what we've done here is we've taken our constraint. Well, first of all, we derived our constraint, you know, based on the net moment at the hip joint, and then we've kind of transformed it into this vector matrix form that we're going to plug directly into the function. Okay. Okay, and so if you think back to the first code that we went over today, this is actually the exact form that we had back then too. I just kind of glossed over it just because, you know, we didn't have time to talk about the formatting. But this is kind of the reason why we format it in this way. Okay, and this is kind of the standard way that MATLAB accepts these kind of equality or inequality constraints if they are in linear form, which is exactly like this. Okay. All right, any questions on this? Okay. All right, so that is the net moment at the hip. We also need equations for the net moment at the knee and the ankle, but they're going to have similar forms. Okay. The only difference is that the moment arm in the equations in the matrices are going to be different. Okay. And in fact, because each of these constraints are linear equations, we can combine them all into one big matrix. And so the matrix looks like the following. So we have M hip, M knee, M ankle. Okay, this is equal to a very large matrix here. Okay. So this matrix here is a 3x9 matrix of moment arms. Okay. Where each row corresponds to the moment arm for moment arms for a specific joint. Okay. So that first row would be exactly this vector that we have up here, right? So the first row corresponds to the moment arm at the hip. And so this is going to be minus 0.056, minus 0.054, 0, 0.043, 0.049, 0, 0, 0, 0. Okay. And then the second and third row, we're going to need the moment arms for the knee and the ankle. Okay. And then multiplied by this are going to be the vector of all of our unknowns. Okay. So we have F1, F2, F3, F4, F5, F6, F7, F8, F9. Okay. All right, so what we have right here, this is the matrix form of our constraints. Okay. And in terms of what you feed into MATLAB, right, eventually this is going to be fed into our function fmin con, right? And so we need to feed it two things. We need to feed this, and we need to feed this in. Okay. And I'll show you the code in a second, so you can kind of see where they get put. All right. Any questions on this before we hop into the code?
Install it, like reinstall it, otherwise it'll let you do it for the first one.
I see. That's okay. I think we'll just go over the code. But thanks for offering that. Okay, so let's take a look at the code. Okay, so we're gonna get the second one here. It's the wrong one. Okay. All right, so this code's a little bit longer than the first one here, but you're going to see that all the sections and all the setup is exactly the same. The biggest difference being that first of all we have 9 muscles that we need to solve for, and we have 3 constraint equations. Okay, but the format of the constraint equations is going to be kind of exactly as we talked about. Okay, so section 1 is the same. Section 1, we're going to find the maximum values for each of these forces here. Right. I also put a legend up here just so that you know. Okay. Section 2, we're defining the objective function. So this is kind of what we talked about before. So these are all the different, you know, muscle forces here, which 9 divided by their respective maximums, okay? Section 3 here is where we're defining the constraints, okay? And so you can see here we have the moment arms for the hip, the moment arms for the knee, the moment arms for the ankle, okay? And here I've given to you kind of the net moment at the hip joint at the ankle, okay? And then we also, and then in order for this to work with F min con, we need to put this all into a single matrix. And so that's what these 2 lines are doing here. Okay, so this section 3 here is kind of exactly kind of what we just spent the last 20 minutes talking about. Okay. Okay, section 4, we have our initial guess. We're just using dummy variables here as well. Section 5, we're setting the upper and lower bound, same as before. Okay. And then finally, section 6, this is where we run the optimization. Okay, so we're given the we feed it the objective function, we feed it the initial guess, we give it the moment arms matrix, we give it the net joint moments, the upper and lower bounds. Okay. Okay. And so if you run this code on your own, so the answer is given to you in the notes itself. But you know, I think it'll be fun to kind of run this yourself and try it and see kind of what you get. Okay. But this code's all ready to go, so you don't have to change anything. But you know, if you wanted to use this code if you wanted to run optimization for your final project, you know, this code will probably be a little bit more helpful because, you know, so just kind of based on looking at kind of what everyone's doing, you're probably going to be in a little bit more of a complex situation like this. Okay. So you can use this code as a template and then just kind of change things for your own specific project, you know, for the moment arms, for the net moments, and the muscle maximums and things like that. Okay. All right, any questions on this? Okay, all right, so that's all we got. That's all I got for today. And so when we come back on Monday, we have final projects, final presentations, I should say. And so if you hadn't had a chance to pick up your midterm yet, they are up here. If not, thank you guys for coming today. You know, this will be the last time I talk to you. I address everyone as full as a class. And so I just want to say thank you guys for a great semester. It was hectic. I know a lot of things going on this semester, but you know, I appreciate your guys' patience. I appreciate you guys' hard work. You know, working here is not easy. Cal State Fullerton is not the best employer, but you know what keeps me here honestly is you guys. You know, just interacting with you guys and getting to teach you guys and teach you guys something new. So thank you guys for that. Thank you for making this job worth it, and looking forward to your presentations next week.